In the colossal theater of global commodities, one substance reigns supreme. It touches nearly half the products on Earth, but few understand its genesis.
This is the definitive journey. Today, we dissect the rigorous, step-by-step process of transforming the raw, fresh fruit bunch into purified, crude palm oil. Prepare for an industrial odyssey.
The beginning, harvesting. Workers select only fully mature bunches, identified by loose fruitlets falling naturally from the spikelets.
Speed is paramount. Once harvested, the oil quality rapidly degrades due to enzymatic activity. The clock is ticking toward the mill gate.
Upon arrival, quality control takes over. Every truck passes through the weighbridge, recording the total yield before processing begins.
Samples are meticulously inspected for maturity, damage, and contamination. Only the freshest, highest quality fruit enters the system.
The FFB is then tipped into the reception ramp, ready to be channeled into the sterilization phase, the critical first step inside the mill. Step 1. Sterilization. This high-pressure steam treatment serves two vital functions: deactivating harmful lipase enzymes and loosening the fruitlets. The FFB is loaded into sturdy steel cages, which are then pushed into the sterilizer vessels, sealing them for the intense thermal process. Superheated steam, often generated by burning biomass waste from the mill itself, is injected, raising the temperature well above boiling. This high-pressure cooking cycle ensures that the oil, which is naturally trapped in the fruit cells, is conditioned for efficient release.
Deactivating the lipase enzyme prevents the rapid breakdown of oil into free fatty acids. High FFA levels significantly reduce the final oil quality and market value.
After multiple steaming cycles, the pressure is gradually released. The fruitlets are now significantly softened and detached from the bunch structure. Precision timing is vital. Sterilization typically lasts between 75 and 90 minutes, depending on the mill setup and fruit characteristics. The cages exit the immense vessels. They are now prepared for the next aggressive mechanical stage, threshing. Step 2. Threshing. The objective is brutally simple: separate every single fruitlet from the heavy, woody bunch stalks. The rotary thresher drum is a powerful, rotating cage equipped with internal baffles that spin and agitate the bunches violently. The mechanical impact causes the loosened fruitlets to fall through the perforated walls of the drum, while the stalks remain inside. Once completely stripped, the remaining empty fruit bunches, or EFB, are ejected and conveyed for downstream usage. The EFB, rich in potassium and nutrients, is often returned to the plantation as natural mulch or incinerated as boiler fuel, minimizing waste. Meanwhile, the released fruitlets are channeled onward. They are visually intact, but now preconditioned for the crucial digestion stage. Step 3. Digestion. This is where the cell structure containing the oil is finally prepared for complete breakdown. The fruitlets are fed into the digesters, where heavy rotating arms vigorously mash them into a uniform pulp, or mash. Continuous heating, often exceeding 90 degrees Celsius, softens the pulp further, ensuring maximum liberation of the oil within the mesocarp fiber. The purpose of digestion is to achieve homogeneity, reducing the risk of fiber blocks and ensuring that the subsequent pressing stage is optimally effective.
The mash consists of oil, moisture, fibrous material, and the hard nuts, all combined into a thick slurry. It is now primed for extraction. Step 4. Pressing. This is the heart of the mill, where mechanical force separates the oil from the solid materials. The mash is subjected to immense pressure exerted by powerful rotating twin screws. The resistance separates the fluid crude oil from the remaining cake. Witness the flow. The rich, reddish-orange crude palm oil, or CPO, gushes out through perforated plates at the bottom of the press cage. Simultaneously, the residual fiber and nuts, known as the press cake, are pushed out the other end, ready for further processing. A sophisticated system ensures minimal oil loss. The pressing efficiency directly determines the final profitability of the operation.
The crude oil collected at this stage is far from finished. It is a mixture of pure oil, water, solid residues, and non-oily contaminants.
Step 5. Clarification. This is the purification phase, separating the valuable oil from the undesirable sludge and water.
The CPO mixture is first diluted with hot water and then pumped into large heated clarifier tanks where gravity becomes the main actor.
Due to density differences, the lighter, purer oil floats to the top, while the heavier sludge, composed of water and solids, sinks to the bottom. Heated coils inside the tanks maintain the temperature, ensuring rapid and effective gravitational separation over several hours. The clarified oil is continuously skimmed from the top layer of the tank, now significantly cleaner but still needing further refinement.
The sludge layer, known as palm oil mill effluent, is drawn off the bottom for environmental treatment and waste recovery. The skimmed oil is then often sent through a centrifuge or purifier, utilizing high speed to spin out any remaining fine solids and water traces. Finally, the purified CPO moves to the vacuum drying system. This critical stage removes residual moisture to meet stringent quality standards. Low moisture content is essential for long-term storage and preventing hydrolysis, ensuring the oil remains stable until it reaches the refinery.
The perfectly refined CPO is now pumped into massive temperature-controlled storage tanks, awaiting bulk shipment across the globe.
But the process is not complete. The fibrous residue from the press still holds immense value, leading us to step 6, kernel recovery. The press cake consists of two main components, the fibrous mesocarp and the hard nut containing the palm kernel. First, the fibers must be separated from the nuts. Specialized pneumatic systems, often called depericarper, use high air velocity for this task.
These separated fibers are immediately channeled to the boiler house. Their high calorific value provides the mill's primary source of energy. The cleaned nuts are then dried. Drying shrinks the kernel slightly inside the shell, making the subsequent cracking stage more effective.
The nuts are fed into the ripple mill or cracker machine, where high-speed impact breaks the incredibly strong shell. This produces a mixture of cracked shells and the valuable inner kernel, which yields the highly sought-after palm kernel oil, or PKO. Separating the kernels from the shells requires precision. Systems utilizing air, density, or both are employed, leveraging their weight difference.
Hydrocyclone systems or clay baths may also be used, where the heavier kernels sink and the lighter shells float in a liquid medium.
These cleaned kernels represent a secondary product stream, often sold separately to specialized refineries for PKO extraction.
The final major byproduct, the cracked shells, are high-grade biomass fuel. They join the fiber, completing the mill's self-sustaining energy loop. Returning briefly to the sludge, the POM is treated rigorously. Anaerobic treatment captures methane, a potent greenhouse gas, converting it into renewable energy. This closed-loop system highlights the modern mill's push towards zero waste and maximum resource utilization, driving efficiency. The entire complex operation demands constant vigilance. Temperature, pressure, flow rate, and moisture content are measured every moment. A tiny deviation can ruin tons of product, underlining the expertise required to manage these immense industrial forces. From the humble fruit bunch, we extract two major products: crude palm oil from the outer pulp and palm kernel oil from the inner seed. CPO is a staple for cooking, biofuel, and thousands of industrial applications. PKO is prized in cosmetics and confectionery for its unique properties. The process we have witnessed is the engine of a global supply chain driven by the ceaseless demand for efficient, versatile vegetable oil. Understanding this complexity is crucial. It's an operation of staggering scale, balancing efficiency with resource management. The precision engineering required to handle highly corrosive, high-temperature fluids and high-pressure steam is monumental. Every fiber, every shell, and every drop of water is accounted for, maximizing yield and minimizing environmental footprint.
The final product specifications often dictate the intensity of the drying and purification stages, ensuring consumer safety and regulatory compliance.
The journey of the fruit bunch is complete. It has endured intense heat, tremendous pressure, and sophisticated separation techniques. This cycle repeats tirelessly, 24 hours a day, driven by the global need for this unparalleled source of fat and energy.
We have peered behind the curtain of industry, witnessing the raw mechanics of modern resource extraction. The scale is immense, the stakes are high, and the science is precise.
Thank you for joining us on this deep dive into the industrial production of palm oil. What other colossal processes should we uncover next? If you found this cinematic explanation valuable, lend us your support and help us continue generating these detailed explorations.
Every like fuels our research, pushing us to deliver more expert industrial breakdowns.
Your engagement ensures the depth and quality of our future reports remain high. Do you have further questions about oil milling, refinement, or the global supply chain? Drop them in the comments below.
We love reading your hypotheses and suggestions for the next complex subject we must tackle. Don't forget to like and subscribe for more updates. Join our journey as we reveal the hidden mechanisms of the modern world.
Thank you, and we'll see you in the next monumental investigation.